Parametric Equations, Chapter 8. So parametric equations are just a different alternative way of expressing a function. You are going to always have two such equations. For example, x could be a function of p of t and y a function q of t. So you are introducing an extra variable. T could be time, and you simply do them separately. So you will have three variables going on and two equations with a connecting variable t. Very often we use t, k, we could use theta or alpha or any Greek letter if you are going to use trig equations. It's possible to combine these two equations to form another equation, which is called a Cartesian equation, by eliminating the variable t. So we'll practice this idea in a moment. If you do get an equation of a function just in terms of y and x, and very often it is possible to make y the subject, sometimes it's not, but as long as there is x and y involved only, then it's called a Cartesian equation. If there are two equations, they are called parametric equations. So the first skill you need to practice is how to convert parametric equations to Cartesian equations. So you do that by eliminating t, variable t. So here's example 1. You've got x equals 2t and also y equals t squared. T is restricted to be between -3 and 3 only, not including the end values. So to find the Cartesian equation of this curve, very often they will tell you if they want the equation to be in y equals form. So if that's the case, we are going to rearrange our x equation to find what t is in terms of x and then sub it into the y equation. So if we rearrange x equals 2t, we are going to obtain t is equal to x over 2, and this is going to be substituted into the equation for y, so y equals t squared. So you're going to obtain y equals to x over 2 squared, which means we have y equals to 1/4 of x squared. So that's a quadratic function. Very often you will be asked to describe the domain and the range of this function. So remember, the domain simply tells you what are the x possible values of x. So what you can do is just imagine having a sketch, x equals 2t for the domain. If you draw the sketch of that function, this is just a straight line. If you plot t's on the horizontal axis and x on the vertical one with a gradient 2. However, we are starting from -3. So if we put -3 here, up to 3, not including the end point. So this is my graph of x equals 2t, be from -3 to 3. Now when t is equal to -3, x is going to be -6. And when t is equal to 3, x is equal to 2 times 3, which is 6. So what are the possible values of x? And this will give me the domain. So the possible values of x are all the values between -6 and 6. So x between -6 and 6, not including the -6 and 6 because t was not equal to -3 or 3. So this is the domain. So when you're going to find the domain, it's going to be quick to consider the function in terms of t, then imagine sketching it and finding what are the possible values of x. So effectively looking at the range of that particular function to describe the domain of the function that joins these two equations together. The range, we're going to look at y equals t squared for the range. So let's just find a different piece of paper to do that so you can see it a bit better. So for the range, we are going to consider y equals t squared. So y is equal to t squared when t is between -3 and 3. So remember the quadratic, you need to be extra careful. It's always a good idea to sketch it. So because this is t and this is y on the vertical axis, so t is on the horizontal. So if I put -3 into y equals t squared, in fact if I put plus or -3, I will have the answer of 9. So these values here of those points are -3, 9 and 3, 9. There you go. So that curve, what are the possible y values that I can get? Well, I'll definitely be hitting 0 here for y, and then going all the way up to 9, not including 9 because neither -3 or 3 were included. So the range, which are my possible y values, are everything from 0 up to 9. So that's the range. And finally, for part C, we are going to sketch our curve. So we have found the quadratic equation to be a quarter of x squared. So if I sketch that quadratic on the domain, which the domain, remember, was from -6 to 6, I'm going to sketch this quadratic from -6 to 6 as well. So it's going to be a nice smiley function. Now it's the y value here is the lowest value 0, the highest should be 9 because we found 9 here. But let's just double check by substituting x equals minus or plus 6 into this equation. So y is going to be equal to a quarter times 36, which is indeed 9. So that value here is 9. So we've sketched the graph of our function that is described by x equals to 2t and y equals to t squared for t between -3 and 3. There you go. So next example is example 2. So here we have two functions, a natural logarithm of t plus 3, so x equals ln t plus 3, and y equals to 1 over t plus 5, when t is restricted above -2 only. Okay, so the first task is to find its Cartesian equation in the form of y equals f of x, and then also in here they're asking us to find the value of k. So they are asking us to describe the domain. So the first thing, remember, to find the Cartesian equations from parametric equations, we need to eliminate t. So the best thing, because we want to have it in y equals form, we are going to rearrange the x equation to find t and then substitute it into y. So let's rearrange x equals ln t plus 3. So give it e, so it's e to the power of x is equal to e to the power of ln t plus 3. I'll do it long way, but normally just put e to the power of x equals to t plus 3. They cancel, neutralize each other, so because they are inverses of each other, so that e to the power of x is t plus 3. So t can be replaced by e to the power of x minus 3. So now we are ready to substitute it into the y. Into y equals 1 over t plus 5. Okay, so y is equal to 1 over e to the power of x minus 3, and then you still have plus 5 in the denominator. So let's just tidy this up. Got 1 over e to the power of x plus 2. And this is our answer to part A, which is the Cartesian equation. So let's go and answer this question about the domain. So what is the domain? So over here we are going to look at our original function, x equals ln t plus 3, and we are going to consider what happens when t is greater than minus 2. So substitute that. So because the range of this function is going to represent the domain of the combined function. So if I look at x equals ln t plus 3, let's substitute t equals to minus 2 into this. So you are going to get ln of minus 2 plus 3. That gives me ln 1. ln 1 is 0. Okay, so that, although this point is not going to belong to our domain because t is not equal to minus 2, this is going to be a cut-off point. So my possible values of x are either going to be less than 0 or greater than 0, because you should know that when you sketch ln of anything, if provided the all possible values of t are considered, you're going to get all real values, so the whole of y-axis. I will sketch it in a minute for you. But if you want to consider whether it's going to be greater or less than 0, try another value of t as long as it's greater than minus 2. So try t is equal to maybe minus 1, or t is equal to 10, for example, or 0. So if t is equal to minus 1, then x is going to be equal to ln of minus 1 plus 3, so ln 2. So let's have a look. So let's just get the, there you go, ln 2. Okay, so that's 0.69. So clearly it's getting smaller. Well, it's getting bigger because we had 0 before, now it's bigger. Let's try 10. So if I put 10 plus 3, so ln 13. So what do I get if I put ln 13? Okay, a bigger number. If you remember, ln function grows steadily, is an increasing function, but really slowly. So I'm confident those values are getting greater than 0. So x's are going to be greater than 0 because that's the cutting off point. So that tells me k is equal to 0, and that is the domain. I promised I would sketch this function for you. So if I asked you to sketch it, and you should be confident that you can sketch any ln function, even transformed ln function. So if it's ln t, then the asymptote would be the vertical axis, which happens to be x-axis over here, but it's shifted 3 units left, so asymptote will go to minus 3. So that is going to be x equals minus 3. So remember, ln shape goes like this. Where will it cross the t-axis, the horizontal axis? So it always crosses it when your x is replaced with 0 here. Normally it's y. So when ln t plus 3 is equal to 0, and that happens for, if you give it an e, it's going to be e to the power of 0, which is 1. So it's going to be 1 minus 3, which is minus 2. So this value is minus 2. Your ln x is going to be 0 whenever this is equal to 1, because ln of 1 is 0. So this is your function. Okay, you can work this value as well if you wanted to, but this would be if it was described from -3 upwards, but we have our t from -2. So if we got rid of the bottom part from our curve, we are talking about only these values of x greater than 0. So you only have that graph. Okay, so we also been asked to find the range of f of x. So let's have a look at the range. So the range is considering the graph 1 over t plus 5 for t greater than -2. This is a very important question. Should be able to sketch this function if it's defined for all possible values of t. So remember, the asymptote is always whenever you make that bracket equal to 0. If you think about it, it's if you can sketch ln t, x equals ln t, then it would look like this. Okay, so it's the asymptote is the vertical axis, which happens to be x, and the horizontal axis is going to be t's. So, and then over here, it always crosses the horizontal axis at whenever t is equal to 1. So whatever natural log is of is equal to 1. This one here is clearly shifted 3 units, and I said if you make that equal to 0, you will get -3. So that is where the asymptote is at, this one is t, this is x, at t equals to -3. And then because you haven't done any transformations, just shifting to the left, the shape will be the same as this function over here. So this value I predicted to be -2 because it used to be at 1. If you shifted 3 to the left, it will go to -2. If you want to double check, you're going to try and solve it when this is equal to 0. So it's when you're making, normally it will be the y-axis, but this time it's x, when x is going to be 0. So you get t plus 3 is equal to e to the power of 0, which is 1. So t plus 3 is equal to 1, giving me t equal to -2, confirming this value over here. Not really interested in this intercept. Because our t's are from -2 onwards, so really the only part of the graph that we are interested in is this part, which is above the t-axis. So it's all the x's over here are greater than 0. And that is the domain. Splendid. So the next part, they ask us to find the range as well. So let's have a look at the actual parametric equation that describes the y coordinates. So y follow 1 over t plus 5. So t plus 5, 1 over t plus 5, so reciprocal graph is always, together with a quadratic, the one that can cause problems when identifying the domain or range of. So I think it's always a good idea to sketch this graph, but also put some values in. So let me just put some values in. So if I put the -2 in, what will I get for my y? So this is going to be 1 over -2 plus 5, which is 1/3. Then I could try a different value. Let's try 0. Then you will have y is equal to 0 plus 5, so it's 1/5. So 1/3 is bigger than 1/5. Let's try a different value. Let's put something even bigger. Maybe put 5. Then you have 1 over 5 plus 5, so it's 1/10. Well, that's getting smaller. Okay, so the values are getting smaller. So you might be thinking the possible values of y will be less than 1/3, not equal to 1/3. But this is where you don't stop. If I try to put a really big number for t, so always for reciprocal try something very large, so let's put, I don't know, 100,000, then you will have 100,005. And if I put this into the calculator, you will have 1 over 100,005, so it's 1 over 100,005. You will see a very tiny number. You could see that 9 is going to be in the 6th decimal place, so it's going to be 0.12345 6 9 9, tiny number, almost 0. So that tells me that you are going to get closer and closer to 0, but never get to 0, because you will be always dividing 1 by a number, so you'll never actually get the answer of 0. So this is what I think it will be. But like I said, it's always a good idea to sketch this reciprocal graph, because it's not a difficult graph to sketch. So it's just 1 over t would be over here, shifted 5 left. Okay, so -5. So let's put this value. We remember this is t's and y's here, so t is equal to -5, and it's just a normal reciprocal graph with 2 branches. So this would be, if you, the only restriction would be t cannot be equal to -5, so you had all possible values for t. But we want to actually have a part of the graph starting from when t is -2, so somewhere here. So -2 will take you to that point, and that point over here was equal to 1/3. So the only graph that we are interested in this question is anything that you obtain by considering values of t greater than -2. So just these values here. So that is the part of the graph that you are going to look at. So if you imagine getting rid of the rest of the graph, you are going to have anything on the y-axis between 0 and 1/3. So that confirms the range to be 0 up to 1/3.